lovely Wednesday morning.
Lovely.
All right. Yeah, we're doing something, huh? All right. So I'm gonna just kind of pick up where we had left off last time. All right. So we were in the midst of this example, and Mr. Kulik did something dumb, going from this step to this step, that we should talk about here as a group because it's an easy mistake to make. And it's because xi has a very specific definition in here. That xi should be a times I delta x. So in this case, that's going to be 0 plus 3i over n, or just 3i over n. So when I do f of xi, I'm really doing f of 3i over n. So when I plug in that to my f of x, this piece should be 3i over n cubed plus 6 times 3i over n. And I'm just going to erase everything from here to just fix it. Is everybody okay? And we'll finish this problem up and then we'll continue on. All right. So I noticed it right as people were walking out. I'm like, why does this look like it's heading in the right direction? I'm like, oh, I am super dumb. So I made my dumb note for myself so I didn't forget to come back and fix this today. All right. So just like we did yesterday, the 3 over n doesn't have any i's in it. So I can just kind of pull that outside the summation, but it still needs to be left inside of the limit because the limit is in terms of n. If I simplify this, that's going to be 27i cubed over n cubed plus 18i over n. Everybody's okay with that? And now I'm going to use my summation rules. So if I go back and I look at my summation properties here, where are you guys? There they are. I'm going to distribute my sum through the addition. And then I'm going to pull my constants out front of the summations. Everybody's okay with that? So I'm going to do that all in one step here. So I'm going to have 27 over n cubed. They're all constants with respect to the summation because the variable in the summation is I. So on the second term, I can pull out 18 over n. Blake?
So maybe I'm missing something, but so you're able to plot the n in those summations, but isn't n still like inherently a variable because you're finding the limit of it?
Yes, so the n needs to stay inside of the limit because that's the variable with respect to the limit. The sums, the variables are with respect to I. So anything that's not an I can consider a constant and pull to the front of the summations
Yes.
But that's all still packed inside of the limit.
Okay, cool. That makes sense.
And these are really excellent questions, right? Like making sure I understand the notation and how to interpret the symbols and like what can I do or what can't I do. Really important. Like how do you know that that's the n is a constant with respect to the summation versus, the limit or whatever. And it's just, you look at the index there and it tells you what the variable is. Okay. Now I notice that, hey, this and this, I have a formula for. If I go back and I look at my properties, the sum from 1 to n of I is n times n plus 1 over 2. And the sum from 1 to n of I cubed is n times n plus 1 over 2 squared. So I'm going to go ahead and drop those two formulas in place of the summations. So go back to our problem here. Notice that what we're doing here, I'm going to distribute this through at the same time, just clean this up a little bit. Uh, 18 times 3 is 54, I think. Everybody so far so good? Okay. All right. So I'm going to go ahead and just kind of multiply these fractions together. So I'm going to expand the one with the squared and then multiply the two fractions just to make a single fraction for each term. So I'm going to have 81 times n to the fourth plus 2n cubed plus n squared all over 2n to the fourth. And then over here I'm going to have 54 n squared plus n over 2, that should be 4, excuse me, 2n squared. Blake?
So going back to the actual formulas that you plugged in for I cubed and I, is there an advantage to having it not just be n squared plus n over 2 and having it be n times n plus 1 over 2?
Well, I'm about to do the limits here, so that helps if my expression looks like a polynomial rather than like a factored form.
Yeah. Okay.
The limit is just easier to deal with that way. Because what I'm going to notice here, to shortcut this up, the degree of the polynomial is the same in the numerator and denominator for each of these limits. So if I evaluate this limit, I can just do that. Right, if I multiply the top one by 1 over n to the fourth, or the first fraction by 1 over n to the fourth, everything drops out except for the leading coefficient. And I do the same thing, 1 over n squared on the second one, everything drops out except for the leading coefficients. And we're done, right? We just make a common denominator. And we're finished. Now, we were able to accomplish this using this method, but we relied on being able to calculate those sums, like having a formula to do that, convert that sum into just an expression in terms of n, right? If you can't do that, we're in a whole heap of problems. Mia? So I just like imagine I multiplied this by like 1 over n to the 4th to the top and bottom. When I distribute that through, this just becomes a 1, 2 over n, like 1 over n squared. And then when I do the limit, all the things with the n's in the denominator just go to 0. So I'm just left with 81 over 4. And I did the same thing over here. I just did 1 over n squareds. You could do L'Hopital a bunch of times too if you want. Like, that's fine. You can just look at it like I did, and I'm like, okay, leading coefficients, polynomial over polynomial, if the leading coefficients are the same, it's just leading coefficient over leading coefficient. What kind of whatever way you're thinking about that is okay. Again, we've kind of proven that a couple of times back in like chapter 2. And again, we saw L'Hopital back in chapter 4. Either one of those methods would be appropriate to evaluate those limits. But I just did it the quickest way because this problem was already kind of pretty cumbersome. All right. We're going to do one more example of kind of using this process before we put it away, and in the next section we're going to find a workaround where we don't have to do this and enormously simplify this process. But let's do one more example because this is still stuff that kind of comes up. Mia. Oh, why did I write as subtraction? I don't know. It probably shouldn't have been. Let's look. Why did I write subtraction? Oh, it's because it's supposed to be subtraction in the problem. I just at some point copied it wrong the whole way through. And then I knew what the answer was going to be because I've done this problem already. That's kind of embarrassing. There we go. Yeah, no, for sure. Like, real, legitimate, important questions. Like, if you see me making mistakes, let's find out what's going on. Is it a typo? Is it Mr. Coolidge just boogered something? Is it what's going on? Okay. That probably makes more sense now. Yes, good. All right. So one more example kind of doing this process. In this example, the textbook asks or suggests using a computer algebra system to evaluate the expression. We don't need a computer algebra system to do this. If you do happen to have the like a CAS calculator, like Jackson, I think you have one. You can just like type it in and it'll spit out the answer for you. And I checked, it's okay to use it on the AP exam, so I'm not going to say anything about using it in class. But we can do it by hand also, and I worked it out, and it's doable with all the tools that we have available to us by hand. So we're going to do it by hand, which is really exciting. Now, it was not trivial for me to figure out how to do it by hand. So it was, the algebra gets a little bit hairy in a couple of places, and I have to pull a formula from algebra 2 that maybe we don't remember. But
that the integral from
1 to 3 of e to the x dx. That is correct. So we need to calculate our delta x. So that's that. our xi is a plus I delta x. So that's going to be 1 plus 2I over n. And so if we do our limit, or our integral, I should say, so instead of xi, I'm going to write my expression for xi, and instead of delta x, I'm going to write my expression for delta x. And so I'd say that's probably our answer for part A. Is everybody okay with what we did there? We just basically plugged it into that formula that we had, where the integral is the limit of the sum of f of xi delta x. Okay. So part B says then to evaluate the limit. So I'm going to do a little bit of rearranging here. I'm going to go again. I'm going to take that 2 over x out front. Since it doesn't have an I in it, I can do that. And now what I am going to need to use, pick a different color so we can. So to evaluate that sum now, I remember this formula from Algebra 2. That's the sum of a finite geometric sequence, or I'm sorry, yeah, or a finite geometric series. So that's the tool that I'm going to use to evaluate this. The problem is my function isn't written in the form that I need it to be. Is everybody okay? We can see that. I'm not like just a variable to the, or my exponent isn't a variable minus 1. So I'm going to need to do some fixing on that. So I'm just going to do as a little aside here. I'm going to take that expression, and I'm going to try to rewrite it so that it's in that form, a times b to the I minus 1. So I know that the plus 1 in the exponent, when I multiply things with the same base, I add their exponent. So I can get rid of the plus 1 in my exponent and change it to a times e to the first, right? Because those have the same base. When I'd multiply them together, I'd add their exponent, so I'd get the plus 1 back. Everybody's okay there? And now I'm going to look at this exponent, and I remember that I'm going to think about this as like 2 over n times I. And I remember if I multiply inside of my exponent, that's the same thing as an exponent of an exponent. So I can think about that. Is everybody okay with that? And now I'm going to just tack a +1 and a -1 on the end, because that's the same as doing nothing. I can always do something like that, right? And then I'm going to pull the +1 out. So this is really e to the 1 plus 2 over n times e to the 2 over n to the I minus 1. So this is like my AI, this is like my R. Or I'm sorry, my A1. Oh, and I guess we called it B over there, didn't we? B. Sorry. Is everybody okay with how I've massaged this thing to get it into the formula, or get it in the form that I need so I can apply my formula? All right. So I'm going to go back up here. So we have the limit n approaches infinity of 2 over n, the sum from 1 to n of e to the 1 plus 2 over n times e to the 2 over n to the I minus 1. And now I'm going to go ahead and use my formula for my finite geometric series. So that's going to be e to the 1 plus 2 over n. That's my A1. I have 1 minus e to the 2 over n to the n over 1 minus e to the 2 over n. A second. You type it and you press enter, and it would probably spit it out. I've spit out this already. All right, let's do a little bit of cleanup here before we move on. So I'm just going to write this as like one big fraction here. So in the numerator, I'm going to have a 2 and e to the 1 plus 2 over n. And then I have a times 1 minus e squared on top. On the bottom, I'm going to have n times 1 minus e to the 2 over n. So what I'm going to do now is I'm going to pull out anything that doesn't have an n. Any factors that don't have an n. So I can take out the 2. I can take out an e to the first. And I can take out a 1 minus e squared all from the numerator. What I'm left with in the numerator then is just e to the 2 over n over 1 minus e to the 2 over n. Oops, sorry. N times. I guess I should mention at some point here that I've been doing all this because at this point back here, I noticed that this was indeterminate. So I didn't mention that, but I'm just doing all of this simplifying, trying to get this thing out of an indeterminate form so I can figure out the limit. So I've done this algebra. Now I notice that really my problem is here, where I have infinity times 0. Mackenzie? Well, none of that stuff has an n in it. So those are all just constants with regard to the limit, so I can pull all of that stuff out front. Does that make sense? Okay. So what I'm going to do is I'm going to do the limit of the top, and then we'll do the limit of the bottom. Again, noticing the bottom is in that indeterminate form. So I'm just going to rewrite it so that it's in like a form where I can do L'Hopital to it. The top limit, though, the limit in the numerator, I can evaluate just with direct substitution. What is the limit as n approaches infinity of e to the 2 over n? E to the 0, which is 1, correct? And then the denominator, I'm going to do L'Hopital to it. So the derivative of 1 minus e to the 2n is negative e to the 2n times negative 2 over n squared. And the derivative of 1 over n is negative 1 over n squared. So at this point, I can reduce in the denominator. The n squareds can just go away, which is wonderful because now I've gotten rid of the indeterminate part. So what I'm left with there is I have 3 negative signs, so that's negative. The limit of e to the 2 over n we said was just 1. And then we have just that 2 left over. My limit's gone now. So I can just now kind of simplify what's going on here. So I'll cancel out the 2's. And then I'll divide by that negative 1. And then if I distribute my e through, yeah, because I divided the negative 1 in.
What about to the out front?
Well, you only do it in one place, right? I could make a negative e out front and not switch them, or I can push the negative 1 into the parenthesis and switch them. I chose to switch them inside.
Okay.
It doesn't really matter how you wrote it. I mean, if you want to write it, put the negative sign there and then distribute through, you'll end up with the same thing. That's fine. And this is kind of a nightmare, right? This process, it can be like extremely difficult to the point where this textbook is suggesting like, don't even try to do this by hand, just have the computer do it for you, which is super. What we're going to see in the next section is we're going to eliminate needing to use the sums to evaluate these definite integrals. Cha-ching. We're going to find the workaround. Much in the same way we started taking derivatives, we did the limit of that difference quotient, like f of x plus h minus f of x over h. And that was an incredible hassle for a lot of functions. And then we just learned the derivative rules and like, oh, okay. So like this dramatically simplifies the process here. The same thing's going to happen in the next section, is we're going to dramatically simplify this process. What you're doing right now is you're using like the definition of a definite integral to evaluate the integral. We're going to learn the shortcuts here in another during the next section. There's a little bit more to do in here though. So let's go and look at these. There's more than one way to skin a cat when it comes to this sort of thing. So it says evaluate the following integrals by interpreting each in terms of areas. So remember that the integral is the same as an area under the curve, right? So if I think about the function y equals the square root of 1 minus x squared, I can square both sides. And if I add x squared to both sides, what am I looking at here?
Circle.
Yeah, circle. What are some more details about that circle? What's the radius? 1. And what's the center? 0, 0. So if we think about this then, let me draw that a little bit better. And if I'm looking at the area under the curve from x equals 0 to x equals 1, I'm really just looking at this area. Done. Well, that was a lot easier than having to jump through all those hoops with the sums and doing the summation formulas and all that nonsense. That was pretty straightforward, actually. You just had to recognize that, like, oh, I could just do this geometrically. We're still just talking about the area under a curve. If the function is representing, like, or that integral is representing, like, a geometric figure, I can just go back to geometry land and do this. Blake?
I feel like I'm missing something. So you use like the interval like 0 to 1, so then wouldn't that also include another quadrant?
But what can we say about the y here?
Oh.
The y is positive, so we really don't have anything down at the bottom. So like all that stuff is not applicable. So yeah, I mean, yes, for sure. We didn't make mention of that, and that certainly is a consideration. Yep. Excellent, excellent. Thought process there. It's like, what about the bottom? Okay. The other one is the integral from 0 to 1 of x minus 1 dx. What do you notice this is? the line. So if I look at the graph here, so we start at -1 at 0, and then we're just going up 1. So I have like that, right? So I can just do like A2 minus A1. Why am I subtracting A1? Yeah, because it's negative y values. It's below the x-axis. Exactly right. So what shape are A1 and A2? Triangles. What's the base of A1? What's the height of A1? Okay, so the area for A1 is just 1/2 1 times 1. What's the base for A2? What's the height for A2? 2. So A2 is 1/2, 2 times 2. Mackenzie? Just counting. So I just 1 unit, 2 units. Since I made sure to plot it on a grid, right? Like this is, -1, 1, 2, 1, 2, 3. Wow! So that's cool, right? No big deal there. Blake had mentioned or asked me at the start of class, like, had we talked about the midpoint rule yet? And I was like, no, we didn't finish 5.2 yet. This is the midpoint rule. Remember when we defined our, let's go all the way back here, that the point we're using can be any sample point. So the midpoint is certainly a valid sample point to use. Now, we wouldn't do that if we're doing infinitely many rectangles. It's a hassle, and it doesn't add anything. But if we're doing finitely many rectangles, the midpoint can give us a better approximation than a left-hand rule and a right-hand rule. If one of them I know is going to be, like if the function is always increasing or always decreasing, I know that the left-hand rule, the right-hand rule is always going to be an over or underestimate for the function. But if I'm using a midpoint rule, like my rectangle would look like that, where I have a little part that's underestimated but a little part that's overestimated. So you tend to get a better representation with a midpoint rule as an approximation rather than a left or a right. Okay, so let's do this using the midpoint rule. So delta x is still the same old b minus a over n. And we have a new xi, we're calling xi bar to represent the midpoint on that interval. So if I split up 1 to 2 into 5 pieces, my intervals would be like 1 to 6/5, and then 6/5 to 7/5, 7/5 to 8/5, 8/5 to 9/5, and then 9/5 to 10/5. Those would be my 5 intervals, right? So my midpoint is going to be the average of those. So what's halfway in between 1 and then 1 1/5? How about 1 1/10? Right? So if I do like 1 plus 6/5 divided by 2, if I multiply the top and bottom by 5, I get 5 plus 6 over 10, or 11/10. That's 1 1/5. So let's do a couple and see if we can pick up the pattern, what's going on here, so we don't have to do it for all of them. So again, I'll just multiply the top and bottom by 5. So that's going to be 13/10. And I'm guessing that this is just going to be the same as like is going to be like x1 bar plus I delta x, right? Because it was 1/5 going from x1 to x2. That would track to me. So that's going to mean that my x bars here are going to be 11/10, 13/10, 15/10, 17/10, and then 19/10. So my midpoint rule, my area is going to be base, which is 1/5, or the delta x, times f of, well, let's write it this way. So we have the sum I equals 1 to 5 of delta x times f of xi bar. So that's going to be the same as the sum from 1 to 5 delta x times 1 over xi bar. Mackenzie. Well, I multiplied the top and bottom of like this fraction by 5 to clear the fraction. So that's where the 10 in the denominator is coming from. Is that okay?
Yeah.
The line on top of it?
Yeah.
That's the notation they're using for the midpoint.
Okay.
So just so it's a different notation than like x1 where we're using a left-hand or right-hand endpoint. Like that's an endpoint of an interval. X bar is going to be the midpoint of the first interval. X1 bar is the midpoint of the first one, the first interval. X2 bar is the midpoint of the second interval, etc. So if we do this, we're going to have 1/5 times the reciprocal of each of these. So 10 over 11 plus 10 over 13 plus 10 over 15 plus 10 over 17 plus 10 over 19. At that point, I would it's calculator time for me. I'm not dealing with that many common denominators. So I'm just, I just did a little bit of sneaky factoring to make it easier to type this into my calculator. You could just type it in exactly how it's written if you wanted to. I noticed that there's a greatest common factor of 10 in that sum. So I factored the 10 out front, 10 over 5 to reduce to 2, and then I just saved myself a bunch of buttons to push on my calculator. And probably, let's turn that into a fraction. You little bugger. anyways, whatever. About 0.69 is good enough. It's an approximation anyways, who cares? I really thought that would still output me a fraction, but it didn't want to. I guess it wouldn't be hard to come up with the fraction, but it's going to be a sucky big fraction. Right, it'll be 13 times 15 times 17 times 19 plus 11 times 15 times 17 times 19 plus 11 times 13 times 17 times 19 plus 11 times 13 times 15 times 19 plus 11 times 13 times 15 times 17 all over 11 times 13 times 15 times 17 times 19. Since those are all relatively primes. But that's just like, I guess I could have done that. I didn't want to. Whatever. Who cares? Right? Good enough for us. Nothing wrong with decimals. Okay. This piece is super important going forward. So here we've outlined some properties of definite integrals. So the first one is that if I flip the bounds of integration, so if I have going from b to a, and I switch it from going a to b, the value of the integral changes sign. That's super important. We'll use that a lot, even going forward once we streamline this process and jettison having to do sums. That's a property we'll want to hang on to and remember. For sure, that's a good memorizer. The next property, if we're integrating from just a to a, well, that's a rectangle that has a base of 0. So the area of that should be 0. Not surprising there. And then we have these other 4 properties of integrals. Again, these are all memorizers. What do these remind you a bit of? That looks like the summation property, right? Didn't we say that we can distribute a sum, the sigma across the sum? Or we can distribute a sigma across the difference? Is it surprising that the integral, which is really just a sum, has the sum of the same properties of summations? No, shouldn't be. Again, just like the summation, if we have a constant inside our integral, we can pull that constant out front. 1 is the only one that kind of needs a little bit of explanation. And I'm just going to draw a picture to kind of justify this. And we'll make that C. So if I graph y equals c, that's a constant function. If we're integrating from a to b of that constant function, the base for that is b minus a, and the height of that is c. So that rectangle is c times b minus a. So just a purely geometric explanation on that one.
So is the addition and the subtraction, are those two properties like
really the same thing?
Yeah.
Yes. Yeah. I would have just written it like,
yes, plus or minus?
Yeah. I would have written it that way, but like, hey, whatever, textbook, you can write it the way you want to. When you write the textbook, I guess that's your prerogative, right?
Yeah, exactly.
But yes, you could certainly have noticed that there's no real difference there. Okay. So using these properties, we're going to now evaluate a complicated looking integral like this one, or relatively complicated. So the first property I'm going to use is property 2 that allows me to distribute my integral. Notice that the dx is applied to the entire function, so I have a dx in both integrals. Is everybody okay with that? And then if I look at the second integral, I notice that I have a constant of 3, so I'm going to take that constant out front because there's still some more function left inside. I'm not going to bother doing that with the first integral because there is no x in there, so I don't have to worry about that. So this, using property 1, is going to be c times a minus b and then using now to evaluate this last piece, I am stuck just using my definition of a definite integral. There's no shortcut through that. So the limit as n approaches infinity of the sum from 1 to n of f of xi times delta x So delta x in this case is going to be over n, and delta x, or I'm sorry, xi would be in this case 0, which is a plus I times 1 over n. So just I over n. So 1 over n sum from 1 to n of I over n squared. I over n squared is just I squared over n squared. So the n's I'm going to pull out. And this piece, I have a summation formula for. Let's go back and double check what it is. I think it's n times n plus 1 times 2n plus 1 all over 6. But I want to double check that. Oops. Where are you? Oh, good. I did remember it. Let's see right here. Is it worth memorizing these summation formulas? I would say no. Because we're jettisoning using them real quick. All right, so let's make doing this limit a little bit easier here. If I foiled the numerator out, what's the leading term going to be? be 2n cubed plus some stuff, right? So I notice here that those degrees are the same. So when I evaluate this limit, it's just going to be the leading coefficient over the leading coefficient. Everybody happy with that? So I end up with 4 times 3 plus 1/3, which is just 5. I think we might have even actually done this integral in a previous example. I think the textbook probably chose it because it was one that they just shortcutted to 1/3, but we did it the long way anyways. Oh well. If we'd done it all in like one shot, I would have remembered, but now that I saw that it gave me 1/3, I'm like, I think we did that in section 5.1 or something. Another, again, this is a memorizer, excellent property of definite integrals. If I have the integral of a to c of f of x plus the integral from c to b of f of x, that's the same thing as just the integral from a to b of f of x. So if you think about it, and you have, here's my function f of x. So if I'm talking about this integral plus this integral, that's the same as just, that integral, right? Nobody's shocked at that. Once you draw the picture, it's like, yeah, well, of course it's got to work that way. All right. So let's do a quick example. It says, it is known that the integral from 0 to 10 of f of x dx is 17. The integral from 0 to 8 of f of x dx is 12. Find the integral of from 8 to 10 of f of x dx. So from property 5, we can say the integral from 0 to 10 f of x dx is equal to the integral from 0 to 8 f of x dx plus the integral from 8 to 10 f of x dx. Dx. So I have 17 is equal to 12 plus this integral. So that integral must be 5. Nice and easy, right? Okay. We have some like comparison properties for integrals also. So if my function is positive between value for x is between a and b, then if I calculate the integral, that has to be a positive value also. Everybody's not shocked by that, I hope. If f of x is bigger than g of x from a to b, then the integral of f of x has to be bigger than the integral of g of x over that same interval, which again, hopefully that's not surprising. If the one function is always taller than the other one, its area under that curve definitely has to be bigger than the other one. And then we say that if f of x is bounded between small m and cap m, so that's like a local min and a local max, between the values a and b, then The lower bound for your integral has to be the rectangle formed using the local minimum, and the upper bound has to be a rectangle formed by using the local maximum. So imagine that you have, just to draw a picture here. So let's say that this is, that's A, and this is B. So this value here is like M. So this is M times B minus A. That's going to be a lower bound for our integral. That's going to be an underestimate. And then here, this, oops, I thought I picked a different color. This value here is cap M. So if we look at that area or that rectangle, that's going to be an overestimate for our integral. The area under our curve lies somewhere in between. Is everybody okay with what that's saying? So it says here to use property 8 to estimate the integral from 0 to 1 of e to the negative x squared dx. The key here, what I'm going to do, is I want to figure out, is that something that's always increasing or always decreasing? If it is, then it's easy to find the local min and the local max over that interval because it's just going to be the endpoints of the interval. So e to the negative x looks like this, right? So e to the negative x squared is also going to look basically like that, or close enough. Everybody agree? So it's decreasing. So my cap m is going to be e to the negative 0 squared, which is 1. And my little m is going to be e to the negative 1 squared, which is e to the negative 1. Oops. So I know then that e to the negative 1 times 1 minus 0 is less than or equal to that integral, which is less than or equal to 1 times 1 minus 0. And e to the negative 1, I guess I could give it as a decimal if I wanted to. So what is it? 369 or 368. That's 1. So that integral is bounded somewhere between 0.368 and 1. Notice that the question didn't require me to find the value of the integral. It just wanted an estimate. Well, there's an estimate. Is that okay? So if I did like a rectangle, like a Riemann sum with like, say, 10 rectangles or something, the value I should get should be between those two. And that's that closed up section 5.2. I know some of you guys started 5.2 homeworks already. Do you want to, is there stuff from there that you guys want to talk about for a few? We have what? We have 15 or 20 minutes here. Got a little bit of time. Mia. Okay, so what I relied on was that I knew what the graph of e to the negative x looked like, which is a decreasing function. right? Because e to the x just looks like the increasing version of it. So if I make the x negative, it just kind of like reflects it. Or you can think about it as x is getting really big. That's basically going to 0. So it's going to like 1 or whatever. So what I did then was, since I know that this is decreasing, at whatever the value a is, that's going to be like my cap m. And then whatever the value b is, that's going to be like my little m. So that's what I did, is I just used the first point on my interval to find my a, or to find my cap m, and I used the last point on my interval, the end point of my subinterval, to find my little m. So again, like what I, so I use the 0 there, and then I use the 1 there. Well, if you look at the function, the negative sign is outside of the squared. So that's, I squared and then made it negative. Yeah. As opposed to if it was like negative x squared. But they probably wouldn't write it that way because they just simplify that to x squared, right? Probably wouldn't write it that way, but that's why the negative sign sticks around. Does that feel good? Do you want to just take a minute and look at a couple of these problems from 5.2 and just talk about like how to start things or whatever? We got some time. I don't know. You guys tell me. Or you just like, I'm really cooked right now. That was a lot. I just need some time to process and rest my brain, which is a legitimate place to be at. Like these courses that have a lot of detail that we're asking you to do 80 minutes on. Like 60 minutes is a lot of math. I get it. Mackenzie? Number 1? Sure. I'm just going to do this and put it on a separate page. I don't know why, but felt like the right thing to do. So this says evaluate the Riemann sum for f of x equals yada 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 between 2 and 14 with 6 subintervals, taking the sample points to be left endpoints. Explain with the aid of a diagram what the Riemann sum represents. Okay. Well, I'll start by calculating my delta x. So that's going to be b minus a over n. So that simplifies down to 2. My xi then is going to be I'll write it, a plus I delta x. So that's 2 plus 2i. But since we're talking about left endpoints, we're starting with x0, so 2, and then 4, and then 6, and then 8, and all the way out to 12. So my area is going to be delta x times, well, let's write the sum, sum from 1 to 6 of delta x times f of xi, and f of xi is going to just be done by this. Ooh, so that's really 0 to 5 though, right? With the way I index things. But I'm not really going to think about it that way, even Mackenzie. That's like the sum that I'm doing. But really, I'm just doing delta x times, and then I'm plugging 2 into this. So 3 minus 1/2 times 2 is just 2. And I'll have delta x times plugging 4 into this. So 3 minus 1/2 times 4 is 1. And then 3 minus 1/2 times 6 is 0. And then 3 times 1/2 minus 8 is -1. And I'm just going to kind of keep going. So there's my 6 rectangles. And what do we get here? We get -6 as the answer. And then it says, explain with the aid of a diagram what the Riemann sum represents. So I'll just plot this picture. Oops, that's... All right, so we have the first point is 2, 2. The second point is 4, 1. Then we have 6, 0. And we have 8, -1. 10, -2. 12. That's 2, 4, 6, 8, 10, 12. Okay. Hi.
You want an award for your book? Can we take a picture?
Not right now.
Okay, thank you.
And then if I wanted to, I could keep going. But this is my function. Put one more. Okay. So what we're doing then is we're, building these rectangles. So that's basically what we did for number 1, Mackenzie. So it's all we're doing is we're approximating the area under the curve, where the area under the curve that's below the x-axis, or area between the x-axis and the curve that's below the x-axis is negative, and the area above the curve, or area above the x-axis but below the curve is positive area. And we could actually calculate the area under this curve quite easily geometrically if we had wanted to and not had to approximate it, but that's our approximation. And I would say it's a little bigger than it should be. If we look at our picture, so we have a little bit of an overestimate here, but that's probably about the same as that overestimate there. We have an overestimate here. That's probably the same as that overestimate or that underestimate there. But we're missing 2 more negative slices that don't kind of cancel out. So I'd say that my actual area should be less than -6. Just kind of talking about what I'm seeing. We're no longer talking about the question. I'm just kind of talking about calculus in general. Is that okay? So again, the hard stuff is like actually evaluating the definite integrals using the summation formulas. Like it's just a hassle. Like it's a lot of algebra. It's a lot of like rewriting things, making sure you have the form correct, that you understand what it is that you're writing. That's the hardest part. Theoretically, though, like what we just did here is the idea, right? Which is not so bad. Next time's going to be the big day. Fundamental theorem of calculus, which is a beautiful, beautiful thing, because what it's going to do is we're going to replace this with the antiderivative, which when we did those last semester were massively easier to calculate than trying to evaluate the limit of these sums, right? Now, not all antiderivatives are going to be easy to calculate, but in the beginning they definitely will be. And as we go through the semester, we'll work out the techniques we need to deal with the harder ones. But not every function has an antiderivative, which is rough. All right, I'm done talking. You guys can go. Thanks, though.